Hi and welcome to John's Maths book. In this video, I'm going to be looking at finding the volume of a solid under a paraboloid and above a disk. If you like the video, then please hit the like button, and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. In this exercise, we have a disk which sits under a paraboloid and parallel to the xy plane. The paraboloid is shown here in red. If the disk extends upwards, a cylinder is created shown in blue. The cylinder will intersect with the paraboloid at various points along the surface of the paraboloid. This creates a solid shown here in purple. It's the volume of the solid that we are going to find. Let's now take a look at this structure in 3 dimensions. The green area shown here is the xy plane. If I add a disk parallel to the xy plane and extend in 3 dimensions, we see a cylinder is created. If I now add a paraboloid, a solid is created between the xy plane and the surface of the paraboloid. It's the volume of this solid that we're going to find. Let's now take a closer look at the disk in the xy plane. As you can see, it's a circle of radius 1 and cuts the x-axis at 0 and 2. To find the volume between the surface of the paraboloid and the disk when extended vertically upwards, we'll find the area of the disk and multiply by a height component to find the volume. To facilitate this, I'm going to use polar coordinates. Let's start by converting the equation of the disk region to polar coordinates. To convert from Cartesian coordinates to polar coordinates, we convert xy to r theta. To do this, we substitute r cos theta for x and r sin theta for y. So for our equation x squared plus y squared is equal to 2x, we can substitute r cos theta for x and r sin theta for y, and this will give r squared cos squared theta plus r squared sin squared theta is equal to 2r cos theta. If we now remove the common factor of r squared, we have r squared into the bracket of cos squared theta plus sin squared theta is equal to 2r cos theta. And using the trig identity cos squared theta plus sin squared theta is equal to 1, we're left with r squared is equal to 2r cos theta. Dividing both sides of the equation by r, we get r is equal to 2 cos theta. Now let's look at what we need to do to find the volume. The volume is a double integral over the region R. This will sum infinitesimally small pieces of area, shown here as dA. When we multiply these infinitesimally small pieces of area by a height function, shown here as f of xy, this will give infinitesimally small slices of volume. Let's now take a closer look at what happens when we sum or integrate in the r direction. When we integrate or sum in the r direction, this will represent the inner of the 2 integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each piece of area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate in the r direction, for this exercise we begin where r is equal to 0. And we travel to the edge of the circle, so where r is equal to 2 cos theta, as we saw when we converted the equation of the circle to polar coordinates. If we multiply an infinitesimally small piece of area dA by height, we get an infinitesimally small slice of volume, which is the height function f of xy multiplied by r dr d theta. We can now define the limits of the inner integral. The lower limit is where r is equal to 0, and the upper limit is where r meets the circle, so that's where r is equal to 2 cos theta. I've also replaced dA representing infinitesimally small pieces of area with r dr d theta. I've marked in the inner integral and its limits. I'll deal with the height function f of xy shortly, but let's first find the limits of the outer integral, so that's when r rotates about the angles of theta. To do this, let's first visualize what happens as r rotates about theta across the region R. As r rotates, it begins at theta equals 0 and advances 180 degrees or pi radians, at which point the circular disk has been covered. Each sector represents an angle of d theta. By summing each of the infinitesimally small sectors, we get our total volume as we've multiplied the area by a height function. We do this by integrating beginning at theta equals 0 and ending at theta equals pi. Now let's deal with the height component f of xy. This extends from the xy plane where z equals 0 to where the disk intersects with the paraboloid when extended vertically upwards. In this case, the height function is the equation of the paraboloid, which in Cartesian coordinates is 4 minus x squared minus y squared. Let's now convert the height function to polar coordinates. To do this, we substitute r cos theta for x and r sine theta for y. So substituting in, we get 4 minus r squared cos squared theta minus r squared sine squared theta. Taking out the common factor of r squared, we're left with 4 minus r squared into the bracket of cos squared theta plus sine squared theta. And using the trig identity cos squared theta plus sine squared theta is equal to 1, we're left with 4 minus r squared, which is our height function in polar coordinates. So to find our volume, we need to evaluate the double integral from r equals 0 to r equals 2 cos theta of 4 minus r squared multiplied by r dr. And then the function of theta this produces, we need to integrate between theta is equal to 0 and theta is equal to pi. So let's begin by evaluating the inner integral. So we're going to integrate 4 minus r squared multiplied by r dr between r is 0 and r is 2 cos theta. So the antiderivative of this is 2r squared minus r to the power of 4 divided by 4, and we're going to evaluate this between 0 and 2 cos theta. So if we plug in 2 cos theta, we get 8 cos squared theta minus 4 cos to the power of 4 theta, and if we plug in 0, we subtract 0. So this just leaves 8 cos squared theta minus 4 cos to the power of 4 theta. So now we need to subtract 4 times the integral of cos to the power of 4 theta d theta between theta is 0 and theta is pi from 8 times the integral of cos squared theta d theta between theta is equal to 0 and theta is equal to pi. So the antiderivative of cos squared theta is 1/4 sine 2 theta plus a half theta. We need to evaluate this between 0 and pi and then multiply it by 8. So this gives 8 pi divided by 2 minus 0. And the antiderivative of cos to the power of 4 theta is 3/8 theta plus 1/4 sine 2 theta plus 1/32 multiplied by sine 4 theta. And we need to evaluate this between 0 and pi and then multiply it by 4. So when we do this, we get 12 pi divided by 8 minus 0. So now if we subtract the second bracket from the first bracket, we're left with our final answer of 5 pi divided by 2.